We now have names for the stuff that happens when we change the numbers A, B, C, and D in our sine waves. A, whatever number is sitting out in front of cosine, that's going to tell us the amplitude of the graph. Now, A as a number might be negative. Amplitude is a distance, so we're going to take the absolute value of A. That's the amplitude. The next number we run across is B. So amplitude is a vertical stretch. That's how we want to categorize that. Amplitude is A. This is a vertical stretch. Or the other version of a stretch, a compression. It's a stretch if the amplitude is bigger than 1. It's a compression if the amplitude is less than 1. Because when we multiply something by 1, we make it bigger. When we multiply by something by 1, nothing happens. When we multiply by something less than 1, we make it smaller. So A, the amplitude. The next number we come across is B. Now, the number B is not the period. The number B affects what the period is in some fashion. So B is going to be related to the period, but it's not going to equal the period. And this is our horizontal stretch. Yesterday, we saw when B was equal to 1, the default, the period was 2 pi. We went around the circle 1 time. When we increased B to 2, then the period dropped to just pi. When we increased B to 4, the period dropped again to pi over 2. When we decreased B to 0.5, the period increased to 4 pi. So the way we calculate the period is to take 2 pi and divide it by B. So the period is 2 pi divided by B. So B and the period are going in opposite directions. When B becomes twice as much, the period becomes half as much. Think of B as the number of times we go around the circle. When B is equal to 2, from 0 to 2 pi, we can go around the circle 2 times. When B is equal to 4, we're going around the circle 4 times. So think of it as how many times we'll go around the circle between 0 and 2 pi. The other one that we clearly identified was D. D is just where the middle is. That's our vertical shift. That's the middle. Number D is the vertical shift. That's the middle. The one that we didn't sort out a lot was C. We know that C is the horizontal shift. That's what's left. We've got vertical and horizontal. We got stretch and we got shift. So I've got vertical stretch, horizontal stretch. Vertical shift, the one we're missing is horizontal shift. And that's what C does. C is the horizontal shift. We want to think of we want to think of the phi as where theta starts. We want to think of C as where the graph starts. It's the theta where the graph starts. We had two categories of starting point. And we're writing start in quotes because it's very fishy to say a start when the graphs go on forever in both directions. So here's what we mean. If you recall, I had mentioned that we think of positive cosine as starting at the top. Positive cosine starts at the top. Negative cosine starts at the bottom. That's where we deal with the sine of A. So positive cosine a positive cosine will start we'll have the top, sorry. There's different kinds of starts. There's top, middle, and bottom. So I want to say the positive cosine is at the top when theta equals C. The positive is referring to the sine of A. We drop the sign to figure out what the amplitude is, but we still use whether it's positive or negative. Negative cosine is at the bottom when theta is equal to C. Positive cosine starts at the top. When we say start, we mean C. Positive sine is at the middle going up when theta equals C. And negative sine is at the middle going down . Five things for us to look for: amplitude, vertical shift, period, horizontal shift, start. Even though start is a very fishy thing to say, it goes on forever. It's just where we're focusing. What do we think of as being zero? What's our horizontal zero? The vertical stretch and the vertical shift, those are the easiest ones to sort out. Once we identify that plus D, that's where the middle is. So that's the middle right here. This is at D. All the y coordinates of the points there are y equals D. Then from the middle, we go up the amplitude and down the amplitude. So up at the top, we have D plus A. Down at the bottom, we have D minus A. A is the distance from the middle to the top and from the middle to the bottom. So if we're at the middle is at D, D plus A is the top, D minus A is the bottom. A is this distance. Those are the easiest ones to sort out. If A is positive, at the top is where we're going to have C. And at the next top will be C plus the period. Before that would be C minus the period. But these go on forever. The period is not just read off of the function. The period is 2 pi divided by whatever B is. In degrees, we could have used 360, but we have to do it in radians. So we put C at the top if A is positive. That's positive cosine. If A is negative, then negative cosine starts off at the bottom. So for a cosine, C will either be where the top is or where the bottom is, depending on the sign of A. So these are the 5 things that we need to identify. 5 things that we need to identify. It's really weird to do it this way because we don't have numbers. Yes, let's cut that. Examples with numbers is what's going to be. If we have sine, the only difference comes down to where we decide where to start. We still, on a sine graph, here's a sine graph, I would put C at the middle going up if A is positive. Then I would put C at a middle going down if A is negative. Positive cosine top, negative cosine bottom, positive sign middle going up, negative sign middle going down. Now we might look at this and think, hang on, aren't the cosine and sine just horizontal shifts of each other? If I take a cosine and horizontal shift to change the value of c by a quarter of a period, won't I end up with the sine? And the answer is clearly not, because look, sine has a little red dots, and the cosine had blue dots, so it's completely they're the same. Yes, you can shift a cosine into a sine. This means that depending on what we decide is the starting point, we can describe a sine wave with a sine or a cosine. Moreover, we could do plus or minus cosine or plus or minus sine. There are an infinite number of descriptions for any given sine wave. So good news, we have a lot of ways we can describe a sine wave. Bad news, we have a lot of ways we can describe a sine wave. Okay. How's everybody okay? Everybody looks like this. That's how I can tell I've been talking to you. Actually, I can tell I've been talking too much because I always work under the assumption that I've been talking too much. It's like what I do. I go home and I don't talk at all. It's like chefs that like cook all day. They go home and they don't want to cook. So I'll just fucking get takeout. When we are learning a thing in math, we have to learn it backwards and forwards. So in problem 1, I have given you an equation. I've given you a function. I've asked you to identify things, and then I ask you to label a bunch of points. I've already drawn the skeleton of. You just have to locate where this graph is. And I gave you a positive sign here. Then on the other side, I've gone backwards. I've drawn a sine or cosine. You've got to figure out what the amplitude, period, vertical shift, horizontal shift are, and decide whether you're going to use plus or minus cosine or plus or minus sine, and write an equation for the graph. And then there's another one. The difficult part in problem 2 is that there are 4 different ways we could describe any sine wave: plus or minus cosine, plus or minus sine. You've just got to pick one. All right, so take a few minutes. Think about amplitude, middle, top, bottom, period, horizontal shift, where it starts. Then label a bunch of points. Please. Let's talk a little bit about finding the graph stuff. The most straightforward stuff to find is the vertical stuff, the middle and the amplitude. So you just find the top and the bottom, because those numbers are just sitting right there in the equation. The numbers that aren't exactly sitting right there in the equation are the period, because that's based on the coefficient of theta, which we call B, and the horizontal shift, which is weird because the framing is theta minus C. So the number that comes after we say theta minus, that number is the horizontal shift. So like in this first problem, we have theta minus 1. 1 is the horizontal shift. We're thinking about what will make this theta minus 1, what will make that 0. what will make 0 times pi over 6? Cosine of 0. What is going to give us that cosine of 0 to start at the top? And we have to have theta equal 1 to make that 0 times whatever the b is. Cosine of 0 is top. It was, and in the second one, in b, it says theta plus 1. When we read that as theta minus a negative 1. Or we think, what do we need to have theta, what does theta need to be to 0 out? So I have negative 1 plus 1 is 0, times pi over 8 is still 0. Sine of 0 is the middle. So that's the thinking there. We're reading theta plus 1 as theta minus a negative 1. So when we're trying to identify C, we read what comes after we say theta minus. All right. Any questions? The other thing that's tricky is that we have to remember that there are two things going on with the period. There's the coefficient of theta that's in the equation. There's the period that we need to calculate for the graph. The period is 2 pi over b. That's the number we need for the graph. The period is for the graph. B is for the equation. What we see on the second page. So for example, on the second graph, I gave you half of a period. So here's the top here. This is happening at -1, and this point is happening at 5. So the distance between those points is 6. But this is half of a period. So I need another 6 to get back up to the top. And so the period is 12. That was the tricky thing that I did on the second graph. I only gave you 2 points at the top and then the bottom. So I gave you half of the period. The period is 12. That's the number for the graph. The number that we're going to put into the equation is 2 pi divided by the period. So this second graph has the same period as our first equation, our first graph we did on the other side. So in this, I don't know why my 6 is levitating. 6 is like, oh, I'm rising above all of this. Anyway. So the other thing that we have in this problem, now we've got the period sorted out at pi over 6. We have the top is at, all the y coordinates up here are going to be the same. So the top is at 3. And we can see that the bottom is down here at -7. The middle's not at 0. The middle is halfway between 3 and -7. So the total distance from 3 to 7, or 3 to -7, this total distance is 10. So the distance that we want, half of that, the amplitude is 5. Oh, and the middle was in red. So once we have this total distance from the top to the bottom, since we have that, we have to cut it in half to figure out what the amplitude is. And so half of the 10 is 5. And so that tells us the middle is at 3 minus 5, or -2, or -7 plus 5, which is -2. So there we had to do a little bit more work to find the middle because I didn't give you consecutive points. The vertical stuff is all y coordinate stuff. The horizontal stuff is all x coordinate stuff. The x coordinate is the horizontal coordinate, y coordinate is the vertical coordinate. Any questions? Comments? Slide them on. Are they getting ready to celebrate Pi Day? I don't know if you know this, but there are competitions. I don't know, it's not really a competition, but there is like a world record for remembering the most digits of pi or being able to recite the most digits of pi. I don't know what exactly it is, but I'm pretty sure it's in the thousands. Some person went along and recited thousands of digits of pi. They just remember it, which seems crazy. What's even worse is we have also a similar competition for computers. We have teams using computers to figure out how many digits of pi, just a bunch of digits of pi, to like a ridiculous degree. The number of and then we have to have the computers confirm that they're correct, which is really suspicious. That the computer is like, oh, here's 10 billion digits of pi, and we're like, oh, are you sure, computer? And the computer's like, oh, yeah, totally. Wait, let me verify. Yep, I'm right. And the computer's like, oh, stupid humans, they can't tell. I just started making stuff up. Actually, we know that computers didn't make stuff up because computers can't make stuff up. They just literally can't. If you ask a computer for a random number, it can't come up with a random number. It's just picking something from a list. Now, that might be like score one for the humans, but y'all can't come up with a random number either. So if I ask you to pick a random number, for the most part, you'll pick an integer between 0 and 10. That's just kind of like what happens. Now that I've said that, if I ask you, you might pick something weird. So if someone asks you for a number between 1 and 10, just pick pi. If you think that's too basic, just pick like, pi squared divided by e. And then you could be like, oh, I'm thinking of a number between 1 and 10. Guess what it is, and I'll give you $100. And they'll be like, oh, 7. It's like, oh, nope. And then they can guess all those numbers. And then you can be like, oh, I was thinking of pi squared divided by e. And you're like, well, how am I supposed to guess that? I'm like, oh, you're not. I'm not going to give you $100. That's crazy. If you want to learn a bunch of digits of pi, your calculator does know pi, but only out to a certain amount, 3.141592654, and it's getting the last one wrong. 4, it's not 4. It's not a 4. You could tell it's not a 4 because if you just go to a source with some more digits of pi, like Desmos is like, it's not a 4. It's a 3. You're just saying 4 because the next digit is a 5, and you've rounded it off. Moreover, your calculator knows that this is not the number, that it's not a 4. Because if you subtract, if you take pi and subtract 3.141592654, you don't get 0. Your calculator knows. It knows. There's the 41. And there's the 59 that goes with that 41. So your calculator knows. Moreover, if you switch to this calculator, 3.141592655, and then turn it sideways to get more digits, your phone calculator knows even more digits of pi. This, by the way, is way more digits of pi than anyone could ever possibly need. It's really ridiculous that we've had computers spit out billions of digits of pi. I guess people just have like stuff like nothing else to do. Actually, it's a good test for computers. That's what it's about. As with many things in math, it's not about the answer. It's about the process. Any questions? Here's a fun fact about pi. If you encode yourself in any way into numbers, into a string of numbers in any way that you want. So like if I encode Evan, well, I don't know what letter V is. Is V, what, 20 something? Let's just do by our last name. L is 12, so 1, 2. I'm going to start making myself up. L is 12. E is a 5, A, C is a 3, H is 8 or something like that. And then I'll put like 6, 5, 0, 7, 3, 8, 4, 1, 8, 6. And then I'll come up with a bunch of numbers. The next line of my social security number, I'm not going to write those down. And then, but if you any finite string of numbers of finite length, they show up somewhere in the decimal expansion of pi. I can't tell you where, because it's a secret. I'm just kidding. I mean, you have to find it. But any string of numbers of finite length, it doesn't matter how long it is, shows up in pi. Because pi goes on forever. That's the thing about infinity. It goes on forever, it never repeats, and it never terminates. That's repetitive. It goes on forever, and it never repeats. You know what I mean by repeating? Like 1/3 is 0.3, and it's just a bunch of threes forever. That's a repeating decimal. 1/7. I could never remember. 142,857. And then it repeats. 142,857, 142,857, 142,857. Because if I subtract 0.142857, there's another 1.42857. So these are repeating decimals. Anytime that you have a repeating decimal, we can write that as a fraction. Anytime you can't write it as a fraction, it never repeats and it never stops. That's called being irrational. Any questions about irrational numbers? It's even better than that. It's even weirder than that, because pi is an irrational number, but it's also a transcendental number. We actually call it a transcendental number, which means it's not the solution to some polynomial equation. Like the square root of 2 is irrational, but it's also algebraic, because it's just a solution to a polynomial equation. But pi is a transcendental number. Any questions, comments, slide remarks? That's your DVD bonus material for today. Stuff what you didn't need to know that I'll definitely put on the final exam. It'll be the only question. What kind of number is pi besides irrational? And I'm like, what? It's like, remember that one day I said one time the thing that wasn't going to be on the final? Yeah, I put that on the final. That's like ridiculous. They're like, well, a history test. What was on page 835 in the bottom left corner? All right. I typically don't celebrate Pi Day because I usually write dates the other way around. Today is 14/3/2024. Not for any other reason that it just makes more sense to me that way. Secretly, I don't even do that. Today is 2024/03/14. That actually puts your files in order if you do that. All right. One last thing is when you're writing equations on this other side, when you're writing on this side, when you're writing equations, this second one here, did you use sine or cosine? If by your silence you mean, yeah, that is correct. We could either use sine or cosine. It depends on what we decide is the start. Once we pick a starting point, that tells us what our horizontal shift is going to be and whether we're using plus or minus sine or plus or minus cosine. So if I start here at -1,3, I'm going to say it's a positive cosine with a horizontal shift of -1. But if I'm like, oh, no, that's too obvious. I don't want to do positive cosine. There's already a positive cosine on this side. That's boring. I'm not going to be one of those Brittany and Justin wannabes. I'm going to use this one down here. And so here you would write an equation with a negative cosine. So I'd say negative 5 cosine with a horizontal shift of 5. So it'd say theta minus 5. Here it'd say theta plus 1. This one would say theta minus 5, would be a negative cosine. Or you could be like, oh, I'm going to use the weird stuff in the middle. So you could use a negative sign or a positive sign. Or you could use this positive sign. You have an infinite number of choices. So good news, you have an infinite number of choices. Bad news, you have an infinite number of choices. Any questions? Comment? Yes. Yes. No, it would be a different number, but it would be the same thinking. So like here we have a period of 12. So here I have a positive cosine with a horizontal of -1. But this point here is 11, 3. So I could start here and say it's a positive cosine with a horizontal shift of 11. So it'd be a plus cosine, and then it would say theta minus 11. This would be weird to use this one because this one is closer to 0. Use the one that's closest to 0. But if you don't want to be one of those Brittany and Justin wannabes, flick your hair off to the side, you could be like, oh, theta minus 11. Then you could be different. Or you could do one that's not even here, right? After the 11, 12 units later, we'll be at 23. And then if you really want to freak Jim Carrey's character out from the movie 23, you're going to go, oh, it's a positive cosine with a horizontal shift of 23. And you go, dun, dun, dun. And then are you frightened, Jim Carrey? Has anybody even seen that movie? It's not a movie that with any, there's no particular significance to the number 23. It just happens to be the one that drives Jim Carrey crazy in that particular movie. You know what I mean? So it's not there's nothing special about 23. It's just a number. That's what I'm supposed to say to throw everybody off the trail. I'm just kidding. There's nothing special about 23. The movie's not about math. The movie's about Jim Carrey's character going bonkers. That's it. Any questions? Comments? Snyder Mark. There's also a movie called Pi. Or not called Pi. I think it's called Irrational. It's about a guy that goes insane because he's trying to figure out, like he claims to be able to see patterns in pi. Here's the thing about numbers. If you go looking for a pattern, you'll find it. If you look hard enough, you'll find one, because that's what we do as humans. The pattern doesn't have to represent anything. It's just one that you decided on. Keep that in mind. That's going to do it for today. I will see you all on Tuesday. Everybody have a good weekend. Thanks for playing.